Welcome back to The Explainer. I am so thrilled to have you here today because we are taking a deep dive into something that is literally rewiring our future. Look, if you followed the tech world at all, you've heard nonstop about the explosive growth of artificial intelligence. But today, we're shattering the illusion that the AI revolution is just a software and silicon story. It's actually deeply, intensely physical. Okay, let's dive into this. The real truth is that the digital economy is right now on a high-speed collision course with the physical economy. Every single time we ask an AI model a complex question or generate an image or train a new neural network, we aren't just moving ones and zeros around in the cloud. We're physically pulling electricity from the grid. And as we scale these AI systems up, we are seriously testing the absolute limits of our planetary power infrastructure. Here is our roadmap for today. First, we'll look at why AI is fundamentally a power story. Then we'll check out the grid multiplier effect. After that, we'll dive into mining, what we call the slow machine. Fourth is geography and declining ore grades. And finally, we'll wrap up with the red metal timing gap. All right, section 1, AI is a power story. We really need to completely reframe how we think about these massive data centers popping up everywhere. They aren't just buildings that hold computers. No, large AI campuses are basically electric load factories. Their entire primary function is converting massive amounts of electricity into computation. And I want you to really let this number sink in for a second. According to World Economic Forum and Kearney data, modern data centers are highly mineral intensive. To put it in perspective, an 80-megawatt Microsoft site in Chicago required roughly 2,100 tons of copper to build. That breaks down to about 26 tons of copper, which is roughly the weight of 4 adult elephants, for every single megawatt of capacity. When we start hearing about gigawatt-scale AI campuses being planned, the sheer tonnage of copper required becomes absolutely staggering. You know, the semiconductor chips might get all the glowing headlines, but it's the hidden electrical backbone that actually gets the copper. AI data centers are just incredibly power dense. To keep them running without even a single millisecond of downtime, you need high-voltage lines, redundant transformers, massive battery backup systems, and heavy-duty cooling infrastructure. In short, AI demand translates instantly and directly into heavy electrical equipment demand. Let's move to section 2 and see how this builds, the grid multiplier effect. So the copper story doesn't just magically stop at the chain link fence of the data center. Because an AI campus introduces this massive new load, it mandates huge systemic upgrades to the whole local utility system. Think about the compounding demand happening right now. We aren't just building AI. We are simultaneously trying to roll out electric vehicles, deploy massive renewable energy farms, and electrify heavy industry, all while expanding the grid to handle the whole shebang. These 5 forces are not operating in a vacuum. They heavily overlap. And they are all competing right now for the exact same copper concentrates, the same smelting capacity, and the same refined copper cathode. Which brings us to what we call a shutoff warning, 2,500 gigawatts. The International Energy Agency's 2026 grid analysis found that over 2,500 gigawatts of renewable, storage, and large load projects are currently just stuck in grid queues worldwide. Why? Well, because the local substations are totally maxed out, the power lines are congested, and the transformer order books are completely full. Let's move into section 3, mining, the slow machine. And this brilliantly illustrates the ultimate constraint in this entire system. You see, the digital economy can announce demand basically overnight. A tech CEO can declare a billion-dollar data center project on a Tuesday, no problem. But there's a huge pacing mismatch here. Building that data center takes maybe 1 to 3 years. Upgrading the high-voltage transmission grid to actually power it, that takes 5 to 15 years. But permitting, financing, and constructing a brand new copper mine, that takes 15 years or more. The loads arrive first. The grid needs copper to serve them. And the mines? They arrive dead last. I really want to highlight another serious shutoff warning here. The IEA recently warned that expected mined supply from all currently announced projects could fall 30% short of our primary supply requirements by 2035. That's a massive gap. The development pipeline for new mines is structurally broken. It is bogged down by rising capital costs, intense permitting friction, and extremely strict capital discipline from mining companies. The copper just isn't scheduled to come out of the ground fast enough. Moving right along to section 4, geography and declining ore grades. So you might be wondering, why doesn't a higher price for copper just immediately fix the supply problem? Simply put, because we are witnessing the decline of easy copper. Many of the world's best, easiest-to-reach deposits are getting old, and as these mines mature, their ore grades naturally decline. This means mining companies literally have to dig up, move, and crush significantly more rock just to extract the exact same tonnage of copper. And doing all of that requires vastly more energy and water, often in extremely dry, arid regions like northern Chile. That forces these companies to build highly expensive, energy-intensive ocean desalination plants just to keep the operations running. And then there's the strategic geography of where those rocks actually go. The best geological reserves are naturally concentrated in places like Chile, Peru, and the Democratic Republic of the Congo. But the refining is a totally different story. In 2025, the world produced about 29 million metric tons of refined copper, and China alone produced roughly 14 million of it. You can diversify where you mine the rocks all you want, but if nearly half the world's refining capacity is centralized in one single country, you are looking at a massive structural supply chain vulnerability. Which brings us to our final part, Section 5, the red metal timing gap. Now, what's really interesting about this is how we actually make sense of this impending crisis. Why can the day-to-day news of the commodities market be so deceptive? Well, it really comes down to a battle between massive additions and limited offsets. On one side, you've got heavy, immediate demand additions, things like AI, grid reinforcements, and electric vehicles. On the other side, we have our incredibly slow-moving offsets, sluggish mine growth, limited scrap recycling, substituting with aluminum, or just plain old demand destruction because the price gets too high. If you do the math, the massive additions systematically overwhelm those slow-moving offsets. Now, you might naturally wonder, can't those offsets just save us? Well, recycling is absolutely essential, but it relies on old scrap. The new copper we're putting into wind turbines and data centers right now, that's going to be trapped and working for decades before it can be recycled. What about aluminum? It's cheaper, sure, and it works great for overhead power lines, but it requires much larger cross-sections. In the ultra-dense, extremely space-constrained high-performance world of an AI server room, aluminum substitution physically fails. You literally need copper. It's also worth noting that the International Copper Study Group released a forecast in April 2026 predicting a small, near-term surplus in the refined copper market. But we have to look at the bigger picture here. A short-term surplus from a temporary release of scrap inventory, or maybe a brief dip in manufacturing, does not invalidate the long-term structural crisis. The refined balances we see today are tiny compared to the absolute tsunami of future growth. And hey, even in a global surplus, specific regions will still be completely paralyzed, totally lacking the actual transformers and grid capacity needed to plug in new loads. So the crucial point is this. High copper prices are a market signal. They are not a magic wand. High prices slowly incentivize new mines to be built over the span of a decade, sure, but they immediately raise the cost of the entire energy transition and the global AI build-out today. Every new transformer, every single grid upgrade, and every new data center becomes instantly more expensive. Which leaves us with a pretty profound, maybe even surprising question to consider. We spend so much time obsessing over the latest generation of silicon, but as we accelerate into the age of artificial intelligence, is the ultimate compute bottleneck really the chip, or is it the humble copper wire required to deliver the power? The physical reality required to sustain our digital future is just immense. I highly encourage you to keep exploring these physical supply chains because they are the true foundation of tomorrow's technology. Thanks so much for joining me on this explainer, and keep learning.